Hello everyone, welcome to my talk, and thank you for inviting me to speak at this workshop on structured approaches to robot learning for improved generalization. In this talk, I decided to specifically focus on structured action representations for learning manipulation skills. Let me first say that I'm a huge fan of structured approaches to robot learning, because I think that structured approaches are just the supporting act for the main act, which is generalization. Okay, so let me explain what I mean by this, and let me explain the role of structure in models through the bias-variance trade-off. In robotics, we're constantly using models that identify or encode patterns in data to approximate some real-world process. These models vary in complexity. Models make mistakes if they are too simple or too complex. If they are too simple, they introduce bias by making erroneous assumptions that do not approximate the real-world process well enough. If models are too complex, they can capture more complex processes, but may overfit to training data and thereby suffer high prediction errors due to variance. What you want is to find a model that minimizes bias and variance simultaneously. Traditionally in robotics, we have models based on first principles like physics. These models have typically only very few knobs to tune. These models are typically more on the left side of this graph and therefore suffer from bias by being maybe too simple to capture the complexity of the real world. More recently, many people develop more and more complex data-driven models. These models have an enormous amount of open parameters, which allows them to capture complex patterns in data, but they often suffer from overfitting and thereby to reduce generalization. These data-driven models typically live more on the right side of this graph due to their complexity. The role of structure in robot learning is to decrease the variance or generalization error of a complex model and find a suitable trade-off while not introducing too much bias. Then the question, of course, becomes, what is the right structure in a robot learning problem? Or, on the flip side of this question, what should it be learned? In this talk, I will not provide a definite answer to this question. Rather, I will provide some case studies from my lab's research that provide some answers and insights. Okay, so what could be learned in a manipulation problem? Here, I formalize the problem in a very specific way as an optimal control problem, where you want to find an optimal control sequence, UT, with minimum cost for a system that follows some system dynamics. Now, for this problem, you can learn the dynamics model, you can learn the cost function, you can additionally also learn the state representation, and many people have worked on each of these learning problems. You could also write down the problem differently to show that you could also learn the policy pi directly given state feedback x and some representation that may be learned or not. And this policy directly returns some action. There is, of course, also a lot of work on directly learning such a policy for manipulation and or the state representation. And for getting an overview of this work, check out this great survey by Oliver Kromer, Scott Necum, and George Konidarius. But so let me first talk about structured approaches to learning in the perception part of this problem. So there has been a lot of work on learning latent state representations, including those from my own lab. But this is actually not what I want to focus on in this talk. I want to focus on a different solution that turns out to be extremely useful in robot perception, and that is to learn models that directly map raw sensory data to explicit interpretable state representations X. So these can be, for example, object poses and velocities. And then this function S that does this mapping can be seen as a virtual sensor. Okay, so let me give you an example of how such a system that uses a learned virtual sensor could look like. So this is an example from my own lab for 3D multi-object tracking, in this case for autonomous driving. So what we have done here is to use a standard approach exactly in the way you're supposed to use it. Specifically, we use a comment filter for estimating the pose and size of each actor in the scene, so cars, pedestrian, motorcycles, and so on. And as a sensor, we use a learned 3D object detector that outputs a bunch of noisy detections that are typically corrupted actually with many false positives. We're using MAGV, that was the state of the art at this point. So then we use a standard Mahalanobis distance to find the best matching pairs of predicted and detected objects. And this metric is actually shaped by the noise covariance matrices of the Kalman filter. And these are typically not so straightforward or more or less straightforward to tune. But what we've done is that given a training data set, we estimate the process and observation noise for the Kalman filter that influence basically this distance matrix. And then once you have done the matching between predictions and detections, you can then run the Kalman filter update to get the posterior estimate for the tracks. All right, so how well did we do with this approach? It turns out that this works extremely well, and we actually won the New Scenes Tracking Challenge at the AR Driving Olympics workshop at the 2019 Europes back in December. And so recently we have lost this first place to a method called Centerpoint, which uses essentially a better object detector. So what we found is actually that if we plug the improved detector into the Kalman filter and recalibrate especially the observation noise covariance matrices, we are coming actually close to this performance. So what does this mean? I think the basic recursive filtering methods are actually working quite well, and there's not much value in actually learning how to track them. But what really makes a difference is the quality of the detectors. And I think this is where you can make the real impact. All right, so there is one interesting line of work that goes beyond using a learned model as a virtual sensor. And this is the work of differentiable filters. So in this line of work, you can learn the process and observation model as well as the noise characteristics by imposing the algorithmic prior of recursive filtering. And many people have shown that learning these models within a filtering loop improves generalization compared to unstructured models like LSTMs. There are many interesting papers submitted to these workshops, but I want to point out two papers that are related to this idea of differentiable filters. One of these papers is the work of my student Alina, and she basically provides a tutorial on how to use differentiable filters for a person who wants to try it. And another one is by Michael Zhu, Kevin Murphy, and Rico Jonskowski, and they propose a new way on implementing the resampling step in a differentiable particle filter in a differentiable way. All right, so what I actually wanted to talk about during this talk is not so much about the structure in the perception problem of, so basically on state representation, but rather I want to talk about the influence the action space has on learning a manipulation policy. And this hasn't been looked at a lot, actually. So when we learn new tasks, we connect sensory inputs to actions to create sensory motor loops. And these loops are not always best learned in the same action space. While some tasks are easy to learn and control in joint space, others are easier to define and learn in Cartesian or task spaces. Furthermore, some tasks require not only to learn motion, but also other components like the amount of force to apply on the environment. I will present a study on the effect of action spaces in robot learning. And I'll also introduce a new action space for reinforcement learning, such that the learned policy can regulate end-effector impedance. So in RL, the goal is really to learn these sensory motor loops. In the RL loop, a policy maps observations to actions, A, in some action space. The RL practitioner needs to predefine this action such that it can be mapped into low-level robot commands, and these are often joint torques. Forcing the policy to directly output joint torques, though, for example by doing pixels to torques, can make the problem overly complicated. So imagine a task that is easy to learn in Cartesian space, like spraying a wall. A policy that outputs torque must not only learn to map observations to action, but also learn how to control the robot in Cartesian space. Can we make this simpler for the policy learner? Yes, we can. We can actually factorize the problem into a policy learning problem and a control problem by introducing a controller. A controller is basically an analytically parameterized function that maps from any action space to robot commands, for example, from task space to joint torques. So we factorize the learning problem into policy learning and control. The policy still learns to map observations to actions that are reference signals to the controller. We have seen impressive results of deep reinforcement learning to learn this map even for high-dimensional input images. These actions are mapped from the policy are mapped into low-level robot commands, in our case joint torques, by the controller. And now this factorization allows us to study the influence of action spaces for the performance of reinforcement learning. What action space should we study though? So first, we will study the difference between learning a policy in joint space versus learning a policy in task space. So for example, in joint space, the policy may output joint velocities, and then we could use a derivative controller to generate joint torques. In task space, we may generate End-Effector positions that are then translated, or not positions, but poses that are then translated into joint torques by a standard operational space controller. Second, we will also evaluate when the policy needs to output motion, so desired position, velocity, or acceleration, versus when it also needs to output forces and torques, So we propose to use variable impedance control in End-Effector space as a new action space that a policy outputs in. And this makes the policy able to control the End-Effector impedance. Specifically, it would output the End-Effector position or pose, but also impedance gains, and therefore regulates how compliant and soft the End-Effector is when in contact with the environment. And we will see that this ability is crucial to solve contact-rich tasks. In our experimental evaluation, we try to answer the following questions. First, what is the effect of choosing certain action spaces on the performance of reinforcement learning? Second, does the action space affect how well policies transfer between different robots or from sim to real? And third, what are the benefits of giving the policy the ability to control forces through variable compliance? So to answer this question, we will train agents on a Panda. We will basically train policies on the Panda and Sawyer robot arms in simulation, and we use PPO in all experiments. And since the performance of RL differs for different manipulation tasks, we evaluate in 3 classical tasks in robotics with different levels of contacts and different inputs. The first task here is free space motion, just following a path that is outlined or indicated here by the spheres in the video. And there's no contact, and we use proprioception and information about the trajectory as input. The second task is opening a door to a specific angle, and there is intermittent contact and changing reaction forces as a consequence of the kinematics of this articulated object. As input, we use proprioception and information about the door state. And finally, we have a third task of surface wiping. And basically here the robot has to wipe off all the green spots on the table. And it uses an eraser that is modeled slightly softly. And the task has a lot of contact. So there are lots of experiments in this paper, and I'm not going to be able to present all of them. But I just want to show you the main results. We see that in the contact-rich task, controlling impedance in Cartesian space in this novel action space enables really high reward policies. Other Cartesian compliant controllers with fixed gains also achieve a good performance, but they're not comparable. And joint space actions are simply not well suited for the task as was expected. So in summary, from our experiments, we see that different action spaces are better suited for different tasks. There's no single best actions for all of them, or action space for all of them. We saw that an important factor is the level of contact, and that for contact-rich tasks, controlling impedance, like we do with this action space, is actually essential. Finally, we evaluated transfer for the surface wiping task. With variable impedance, the policy transfers best, although there is some significant drop in performance due to unmodeled contact dynamics. But again, this transfer of a policy that is learned on one robot to another robot is pretty good, and that's not so surprising since we're using a well-studied controller that abstracts the embodiment. In general, learning these tasks in task space enable better translation between robots. And again, unsurprisingly, the policies trained in joint space drop abruptly in performance to almost zero, which is due to the different kinematics of these two robots. And in the last experiments, we tested if the policy trained in simulation transfers to the real world without any retraining. So, and here we show that in 8 out of 10 trials, the robot successfully wiped the table, removing more than 75% of the painted area. So what are the key takeaways of what I presented so far? First, I showed that the choice of the action space for reinforcement learning is really crucial for the success and for the performance of the solution. And also, there is no single task space that works best for all tasks. But second, we saw that policies learned in task space with a proper operational space control formalism transfer better because of the abstraction of the embodiment, which is, again, like expected, but you should think about it. And finally, we saw that the new action space for RL, variable impedance control, and End-Effector space allows the policy to control the amount of force, and that is really crucial for contact-rich tasks. If you're interested in more details on this work and all the experiments, check out this page. And you also find the code on this page. Okay, so let me summarize what I've presented so far. So basically, this in this work, we really just wrap a standard, well-understood controller around an RL policy that solves the hard problem with learning. And the hard problem here is solving a full contact-rich manipulation task with this controller, so basically providing the reference. Let's make this problem more complex. Imagine that you do not only have one arm, but you have multiple fingers that have to move in a coordinated fashion to manipulate an object. When humans manipulate tools, we typically want to move the object to a goal position and orientation without moving contact points on the object. As shown in the first video, the workspace of the object is limited in range. While in the second and third video, the object workspace covers a wider set of possible states by changing contact points. That's a great strategy that we would want to basically have our robots adopt as well. So we decompose our dexterous manipulation action space into 3 key primitives: reposing, sliding, and flipping. These primitives are necessary to change either the contacts or the position of the object to desired position and orientation without dropping the object. So we propose a hierarchical structure leveraging a higher level RL policy that learns how to sample a sequence of low level primitives to reach a desired goal position of the object. Our hypothesis is that the hierarchical structure is necessary to make the task of learning to manipulate the object without dropping it more tractable, and will result in higher quality policies that are easier to train. So we compare our method with an end-to-end RL approach as shown in these videos, and as we can see, our method can continuously hold the object and manipulate it to challenging poses. So in summary, this particular approach makes the following contribution. The object is dropped less often during learning, but also during test time. And the object can be manipulated to more distant and challenging goal locations. And the learned policy is robust to observation noise and can generalize to variations in the object. So what's our methodology? So basically, let me first introduce the three primitives. Suppose we are grasping an object like this one, and the circle here, or the ellipse here, represents the object workspace under this, given these contact points. We have an initial pose and a goal pose inside this ellipse, and we define our first primitive reposing to move the object from one pose to another pose like this. And here on the right, you see basically the control law that we're using to control the fingertip accelerations. So the second primitive we're using is sliding. So suppose the goal pose that we actually want to achieve needs some kind of different contact configuration. And we define the second primitive sliding to slide our finger along the object to change the contact points. And we're using the control law shown here. And now the manipulator can also have multiple ways to grasp the object. For example, grasp pose 1 here represents 2 fingers below the object, while the grasp pose 2 represents 2 fingers above the object. Leveraging these grasp poses, or basically transitioning between them, can increase the reachable workspace. In light of this, we define a third primitive, flipping, to move one finger from one side to another side. So these low-level primitives are all implemented by torque controllers that are inherently robust to noise because of their compliance. And at a higher level, we train a reinforcement learning policy to sequence basically and orchestrate these primitives. Our first experiment shows that our method's performance at reaching desired object poses at the 3 is successful even over different levels of difficulty. The model is evaluated on 500 episodes over 5 random seeds. As the goal becomes harder, the gap in performance between our method and the baseline grows significantly. Observing the test episodes, we found that the end-to-end RL method fails in most cases when flipping is required, indicating that the skill is difficult for RL to learn. We also tested basically a search-based method, and it has a lower drop rate in the medium and hard goal settings than, for example, the end-to-end method. But it struggles at reaching some of the harder tasks, and it may actually be very expensive to roll. So here we visualize an instance of an episode that are a few examples of how our method actually coordinates the finger motion and uses the primitives to reach a particular goal pose for the object. We also evaluated the robustness of our method in the presence of observation noise and inaccurate models of the object's geometry and inertia properties. So, different from end-to-end models, which typically train one policy per object, traditional controllers require some prior knowledge on the robot hand and object. In the real world, object pose estimation may be noisy, and the object and hand models may be inaccurate. So the successful manipulation method should be robust to these real-world effects, and here we just demonstrated that this is the case for our approach. Finally, we test how well our approach does at combining our primitives when we're using a different object from the pole-shaped object. So for manipulating square objects, we found that our method could perform better once releasing one of the contacts was allowed, by making it easier to balance the short objects with just 2 fingers. So our project has demonstrated the usefulness of leveraging predefined low-level manipulation primitives such as reposing, sliding, and flipping in a hybrid approach with reinforcement learning to train goal condition policies that access a wide range of the workspace. Our in-hand manipulation environment, though simple, is challenging for standard RL methods since it's very difficult to explore the workspace widely without dropping the object often or collecting very short trajectories of experience. So the structure has actually been shown to work well in other works as well. So here I'm just showing an example of neural task programming that translates a demonstration into a neural program, and then the low-level action primitives are actually implemented in a similar way as we have done this for more high-level tasks like stacking, pick and place. And of course, our work is also related to this project on learning dexterity by OpenAI that does not use such a hierarchical structure. Of course, this work is extremely impressive, especially because it's demonstrating in-hand manipulation on a real robot, and there are these really interesting manipulation primitives or skills basically emerging. I still want to point out a few differences to our projects. So for example, we do not assume that there is a palm on which the object can land. In fact, in our work, the fingers have to hold the object firmly, and otherwise the object basically drops. And also we have shown that using this hierarchical structure with skills at the lower level reduces training time. So if you're interested in more details in the code of this project, please check out this webpage. So each of these works that I've presented really wrap a standard controller around an RL policy that provides essentially the reference signals for these controllers. And the policy solves the hard problem of finding the next best high-level action in an appropriate action space. The controllers are very well understood and basically track this reference that the policy produces, and since we're using tort control, we basically have inherent robustness due to the compliance of the robot. So in these works, though, the low-level actions are being solved by a given controller because we know how to write them down. However, when the low-level manipulation becomes more complex and therefore difficult to derive manually, learning this low level may actually not be, may be more feasible. One message you should really take away from this is you have to choose your action space carefully, because it actually has influence on how well your RL method is going to do. And you should also use well-understood controllers where possible to learn what is only necessary, and what you will gain is faster learning and better generalization. So with that, I thank you for your attention. I would like to thank all my students and all my collaborators, and of course all my funding sources. Thank you.